Okay, let's get back. Let's get back in the. We talk about transportation. Yesterday we talked about transportation. We talked about composites this morning, and I want to show you a small study we did a few years ago. And there's a company called Fiber Forge in the U.S. And the idea of this company is that they want to make composites for automotive applications. Okay, this is the holy grail for composites, making them in a very inexpensive way so that they can be used in high volume applications, in particular in transportation. And one of the challenges that we've discussed for the last 2 days is cost. Okay, so you have the cost of the raw materials, the fibers, the cost of the matrix, and then you have the cost of manufacturing. How do you make these things in a way that is cost effective? So there is a process called forging. Are you familiar with forging, with metals, metal forging? And that's the same idea. And they say, well, we would like to use a forging process, but we want to use it for composites. And they claim that this process is going to reduce the manufacturing cost in a way that they can use it for transportation. Now, if you want to make an automobile in the US, and I'm sure in Europe is the same, that has composites, you have to show that the structure can absorb sufficient energy during a crash so that the passengers will not be put at risk. So every time you want to have a new structure, you have to go through a series of tests. And in the US, there is an agency called the Federal Highway Security Administration. And they actually do these tests. They take a car and they crash it. They put these dummies inside. I don't know if you have seen the videos. They have these dummies inside the car, and they instrument the dummies with the strain gauges, accelerometer, so they can measure how much force a passenger will absorb during a crash-like scenario. And the same has to be true for composites. So this company wants to get into that business. And what they claim is that they have a way to make tubular structures, okay, for automobiles. And if you look at the structure of an automobile, you have a lot of channels. You have the posts that go next to the windshield. You have the posts that are behind the doors. So there are lots of tubular structures. And they claim that they have a way to make these tubular structures for high energy absorption applications. So they came to work with us at the lab. And we have a machine called the Test Machine for Automotive Crashworthiness. And this is a very unique machine because we can subject structures and materials to very high loading rates. This is like a dynamic testing. And somebody of you was working on dynamic. Was that you working with dynamic testing? So this is very close to what you are doing. And I want to show you how we use that machine for doing this test. Now, again, the implications are very clear because if you can show that these materials can absorb energy, they can be used to manufacture composites for transportation. So this is the idea. They make these tapes, and they call them tape layup. And you can see here the fibers. You see the fibers? How they are aligned in a particular direction. So they have the fibers, and the fibers have a resin. It's a polyethylene type of resin. And they can make this in a flat shape. So they can make these panels. And then using heat and pressure, they can make these shapes. So that's where the forging comes from, where you can have a high impact press, and then you can make these tubular structures. And then you can cut the edges. So once you make this curvature, you cut the edges, and then you have this U shape. And then you take two pieces, and then you bond them, you join them, and now you have a tube. Okay? So now there are many ways to make a tube. There's a process called filament winding, where you can take the fibers, and you can make a tube, and then you introduce the matrix. But they did a calculation. They showed that by making tubes this way, they could save in terms of manufacturing cost. And then the question was, will those tubes have the structural properties necessary to be used in an automotive application. So that's why they came to work with us. So let me show you a couple of videos. So here we have the tube. You see the edge of the tube, okay? And this is a piston. This piston is connected to the machine. So the piston is moving at a very high speed. We have a very high speed camera. So what you're going to see here are very fast frames. We're collecting thousands of frames per second. So the actual test takes just a few milliseconds. But because we take images so fast, you can see the whole process here in slow motion. So I'm going to get the movie going. And now you can see the piston moving down. You see the fibers. You see how the bonding occurs here. It opens up. The fibers start flowering out. So you have a lot of deep bonding here at the interface and then the tube. So this was one type of structure, okay? So as you are compressing it, you're going to see how it delaminates. And then in this case, this is the second sample. So look at the second sample. You see the difference compared to the first sample? In the first sample, you have a lot of deep bonding.
Provides an unrivaled portfolio of advanced composite solutions.
Well, so there it goes again. So this is sample A. And see how much delamination takes place? The fibers are debonding. It opens up. And what we do is we measure the force. We measure the displacement, and that the area under the curve is going to give us, so that's sample A. And then let's look at sample B. So in this case, sample B, the formulation was a little bit different. But see how the interface between the two halves remains more or less bonded. But you can see how the fibers start to debond. And while we were doing these tests, we had an infrared camera, okay? And the infrared camera can be used to measure temperature. So let me show you what we got out of that sample. So now we're measuring temperature. It's a little bit faster. Bright areas correspond to hot zones. So what we got from those experiments was that these systems had very different modes of failure. And in some cases, you have catastrophic failure where the two halves of the tube open up, like in this case. And then you have other cases where these halves remain bonded all the way to the end. These cases where you have partial opening, you can see how the composite opens up. And by using infrared camera, we were able to quantify how much energy in terms of heat was generated as part of this deformation process. If you think about it, every time you have a fiber pulling out of the matrix, that fiber is going to be frictionally moving against the matrix. So that generates a lot of heat. So if you have one of these structures in an automobile and you're in an accident, these structures can absorb and dissipate a lot of energy. And they do it because every time you debond one of these fibers, look at all these fibers, every time you open up this structure, there is so much surface area inside these composites that can absorb a lot of energy, okay? And that's what will save passengers. So when you quantify, when you compare the energy dissipated by these systems with metals, these materials are these materials have twice the amount of energy absorbing capacity compared to steel. And they have half the weight, if not a smaller fraction. And this is exactly what you want in an automotive structure. You have something that will be light, something that's going to be strong, something that's going to be stiff because you don't want your car to be deforming when you are driving at 60 miles an hour. But you also want something that will absorb a lot of energy if you have a type of accident. So it's an example of how we have used mechanical testing, and these are dynamic tests. These results are depending on rate. These are very high rate. This is equivalent to a 40-mile-an-hour type of collision. And what they show is that these materials can absorb a lot of energy. They can be used for automotive applications. So this is an example of how these composites can use for that. Okay, let's show a video. I'm going to show you, we talk about automotive applications. I'm going to show you aerospace applications.
We develop and manufacture lightweight, high-strength components for the automotive and aircraft industries. We support the efficient generation of wind energy, and we invest in the future. The material we work with is carbon. The starting material for our lightweight, high-strength components is a precursor based on acrylic fibers. Complex oxidation and carbonization processes convert this precursor into carbon fiber, a unique material used in high-performance textile products and a wide variety of composite materials. SGL Group is the only European-based carbon fiber producer to cover the entire value chain, from fiber to finished component. Our fabrics made from carbon, glass, or aramid fibers can be matched to any particular application and processed further as required. We produce carbon fiber-based multi-axial fabrics for a wide variety of high-quality products. These fabrics allow us to maximize the application-specific stability and stiffness of components while simultaneously saving material. Carbon fiber composite materials open up new applications where other materials reach their limits. Whether fabric designs with variable fiber orientation are required, or different types of weave combined with high-quality resins, we can match our materials ideally to the needs of our customers. Our core competencies cover the production and further processing of carbon fibers, as well as the engineering of carbon fiber composite materials. This leads to technical innovations, such as the automated braiding process. Despite their tremendous strength, carbon fiber reinforced components are less than half the weight of steel, weigh approximately 30% less than aluminum. In automotive engineering, the drastic weight savings achieved with CFRP components not only bring about new performance records, but also reduce both fuel consumption and CO2 emissions. SGL Group supports this innovation by developing processes suitable for large series production processes. The SGL Group invests in future technologies. With our materials and process know-how, we help increase the efficiency of onshore and offshore wind energy plants. In close cooperation with the wind energy industry, we manufacture rotor blades from fiber-reinforced plastics, lengths of 60 meters and more. These blades are used in state-of-the-art wind turbines to ensure maximum safety and low noise levels combined with high performance and cost-effectiveness. As one of the world's leading manufacturers of carbon, SGL Group covers the entire value chain of carbon fiber products, from the precursor via carbon fibers, fabrics, prepegs, and preforms, to finished components in carbon fiber reinforced plastics, carbon fiber reinforced carbon, or carbon ceramics. Carbon is the key to innovative, efficient, and sustainable solutions for the environment and our future. Carbon is future. SGL, the carbon company.
So, any questions about that video? From carbon fibers all the way to composites, they talk about the whole supply chain. They talk about PAN fibers, polyacrylonitrile precursors. They can make braided structures to make tubes. I show you an example of how this fiber forge company makes tubes in a different way. Again, we're going to talk about wind blades, turbines for wind energy here in a minute. Let me show you another video. This is from Boeing. And this is an example of how we've used composites for in this case, talks about the 787, the Dreamliner. This is probably the most advanced aircraft.
787 built to that Boeing 787. Instead of being implemented with the carbon composites that we're seeing here are the heads of the machines that laid on the tin. Carbon tin comes in rolls like duct tin, is rolled along a surface and laid flat. The carbon fiber is infused with epoxy resin, and this black material on top of this slab is what's being laid. And when they're making a fuselage, they spin a barrel. This is called a mandrel. It's a cylindrical mold, and they lay the tin. There's the tin head machine again, laying the tin in layers one after the other, as the mandrel spins and the fuselage takes shape. You can see it turning as the head works its way along. So they make layers of tin, and when they've got the shape ready, they put it in a giant oven. That's what this is. It's called an autoclave. They've had to build some of the biggest autoclaves in the world for the 787 project. The one in Wichita, for example, is 30 feet in diameter, 70 feet long. They take it out and it's baked hard. Material is black when it's not painted. So you'll see airplanes no longer having the shiny metal unpainted surface, joining two of the fuselage pieces together. There we have the beginning of a Dreamliner. For the first time ever, the wings of a Boeing airplane will be made overseas. Boeing developed in its research center here down in Marginal Way the method for making the wings. This is the composite skin being fitted to the ribs of the airplane. And this picture is in Nagoya, Japan. This is the Japanese now having fully developed the technology. The big blue cylindrical thing there, that's the autoclave. In this plant built just in the 87, the wings slide along in these automated trolleys and slide into the oven. But the very first piece, the first 787 that had to be built, was the center wing box. was first joined, the gap between the fuselage sections. Here are the wings coming on. Look at how slender those wings are. And now here's one of the most difficult pieces to join. It's the horizontal tail. Behind it you can see the APU, the auxiliary power unit, that little curl in the back. That's in Korea. And in this piece of tooling, they will finally join everything together. At the very back you'll see a tower, kind of blue and golden tower that's in there, called the mother of all tooling towers in Boeing's affectionate jargon. And they use that to pull up the vertical fin. You can just see the vertical fin of Dreamliner 1 being attached. That's the only piece of the airplane made by Boeing. It's made in Frederickson near Tacoma. Here are the engines. In this case, Rolls-Royce engines, sent from England to go on the first Dreamliner. The landing gear, made by a French company, Seminarios. And with the big joins made, the plane is ready to move forward to the next position, to start getting all its systems installed and connected. That's Dreamliner 1, just before the rollout 2 years ago. We didn't know then that most of the systems hadn't been installed. Dreamliner 1 rolls out of the factory in 2007 to go across the 526 freeway on the bridge. It didn't paint it. To be painted.
So before we talk about this, why do you think the wings were made in Japan? You know, Boeing can make good stuff. You know, why would they make the wings in Japan? Anybody? I mean, the Japanese are pretty good. I mean, they have a lot of good technique, but you know, this is economics. So there's a Japanese company called ANA, All Nippon Airlines. You know, you have Japan Airlines, then ANA. The agreement between all these companies and Boeing was, we will buy your planes over Airbus, but you have to make the wings in our country. You heard about the auxiliary power unit was made in Korea. Same thing, Korean Airlines. So, you know, we will buy your planes, but you have to make the APU in our country. And that's how it works. If you want to sell planes in China now, the Chinese tell you, you have to make them over here, and you got to hire Chinese engineers and all the manufacturing, all that. You know, that's the way economies work these days. And what's amazing is it's only the tail that was made in Boeing in the Pacific Northwest. Everything else came from different companies. And that's the world economy these days. You know, it's not just Europeans and the U.S. dominating all this. I mean, all these countries that want to buy all these technologies, they have money, and they can place some restrictions and some constraints.
In the beginning of the video, when there was the fuselage rotating,
Mm-hmm.
and there was a machine like, what was doing the machine, like depositing fibers,
Mm-hmm.
or impressing?
Yeah, and that's a good question, and that's what we're going to talk about here for the next session. And that's actually a good question, because there is something called pre-preg, and you probably heard that word a few times. Did you hear about that pre-preg? Actually, the German video talk about pre-preg. Pre-preg is a combination of fibers plus resin. Okay? And this is the resin before it's cured. So if you use an epoxy, let's say that you use an epoxy. To make an epoxy, you need two parts. You need the resin, and then the hardener or the catalyst. So when you make pre-preg, what you have is the fibers plus the resin, and then you already have the catalyst, and you have just a number of hours before this reaction takes place. Now, if you heat up this system to, let's say, 130 degrees C, this reaction between these two components is going to take place very quickly. And then the resin becomes very hard. So what you saw in that rotating video, what you are doing is you are applying a bunch of pre-preg around the cylinder. And then once you have the structure, you take it to the oven. And then the reaction between the resin and the hardener takes place, and then the epoxy becomes hard. Okay? Now, the robot, if you pay attention, the fibers were moving at a different orientation. Okay? And the question is, at what orientation do you make this structure? So, and that's what we're going to be talking about here in a minute. So if you have a cylinder, let's assume that this is the fuselage. If you are flying at 30,000 feet, what type of a stress does the fuselage see? You have to pressurize it, okay? So you have internal pressure, okay? There may be a little bit of torsion, perhaps, maybe some bending. But in the case of the pressure, if you have internal pressure, what's going to happen on the skin of the fuselage? What type of stresses are you going to have? Hoop stresses, they are tensile stress. So you have that the tangential stress is going to be proportional to the pressure. It's going to be proportional to the radius, and then inversely proportional to the thickness. And that's just for the internal pressurization. So you pressurize the airplane, you go to 30,000 feet, and then you have the wings. So the wings are doing this. So you are applying some sort of a stress here. And then the plane may be doing something like this. So you have tensile stresses in this direction, and you could have compressive stresses in this direction. So the state of stress in most of these structures is very complex. And how you place the fibers really is in response to the expected state of stress. And we're going to do that here in a minute. So when the robot goes, you have the mandrel running, and you're applying your pre-preg, this pre-preg gets reoriented in different directions. Sometimes the fibers will be running in this direction. Sometimes the fibers are going to be running in that direction. Sometimes the fibers are going to be running in that direction. In fact, it's going to be a combination of different orientations. And I'm going to show you how that gets determined here in a minute. Okay? So that's a good observation. That's the pre-preg, and that's how it gets applied in the actual system. So, any questions about this? No? Okay.